using point slope form, I would get that. Now the equation of a line normal to P is a line that's perpendicular to this, right? Perpendicular to that, but goes through that point. So that line would go through the same point, but it would be perpendicular to that, so it would have a slope that's opposite or reciprocal to it. So this would be the normal line, okay, which means that it'd be perpendicular to the first one. Okay, so the average rates of change is just a ratio of two changes. So, and it's typically just on some interval given 2 points. So given 2 points, given 2 data points, you could find average speed or average growth rate of population or average rainfall. Average rate of change is the slope of the secant line through those 2 points. So we've covered this before. We got our two forms here and here for that difference quotient. The instantaneous rate of change occurs. So we got average rate of change if we take the average of those two, or excuse me, the slope between those 2 points. The instantaneous rate of change occurs when the change in time, or x, right, change in our independent variable goes to 0. It is the slope of the tangent line. So the instantaneous rate of change is the limit of our difference quotient as h goes to 0 of f of x plus h minus f of x all over h. Okay, and it only exists. This only exists when the limit exists. So the limit as h goes to 0 of all this stuff has to exist. Has to exist in order for there to be instantaneous rate of change. Alright, so let's do this real quick. Let's use the difference quotient real quick to analyze the slope of the graph of that tangent line at the point 24 on y equals x squared. So let me graph it real quick here. Okay, so I drew a graph of the sketch, and I drew a tangent line to that graph in green. I also found f of x and f of x plus h in terms of x, and then f of 2 and f of 2 plus h. And now what we're going to do is we're going to find the slope of the secant line, or excuse me, the slope of the tangent line by taking the limit as h goes to 0 of the difference quotient. So I'm going to take f of 2 plus h. Right? I'm going to take this thing. So f of 2 plus h minus f of 2 all over h. And see what happens here. So the slope of this tangent line looks like the 4's will cancel. It looks like I get, oh boy, h's, one h in the numerator, or in each of those terms, and the h in the denominator to cancel. So it looks like you get 4 plus h. And the limit, I should probably write that out, the limit as h goes to 0 of that, limit as h goes to 0 of 4 plus h, looks like the slope of that tangent line is going to be 4. Okay, on example 2, I want to take a slightly different approach. Okay, we're going to use the same graph. We're now changing this from where x equals 2 to where x equals c. I'm going to keep this in general terms for just a moment. I'm going to take the limit as h goes to 0 of f of x plus h, which we had before, x squared plus 2xh plus h squared minus f of x, which is x squared, over h. Okay, I got that from up here. Alright, now I'm going to simplify this. So I see I get x squared to cancel. It looks like I get an h cancels. So right now I have the limit as h goes to 0 of 2x plus h. Now I wanted this to be evaluated at x equals c. So first thing I'm going to do is as h goes to 0, that's just going to disappear. So I'm going to get 2x. If I want x to equal c, then my slope would be approaching 2c. So whatever my x value is, my slope will be twice as large as that x value. Okay, so now that I have the slope of this tangent line in general terms is 2x, right? We just found that in the last one. Now I can find the tangents to the curve y equals x squared at two separate points. So let's do these in blue and in red. Okay, so in either scenario, all I need is a point and a slope. So I have a point in the first one, be negative 1/2, 1/4. And I can quickly find a slope. So I take that negative 1/2 and I plug it in, and I get negative 1. So now I've got a point and I've got a slope. I can write the equation of the tangent line. Equation of the tangent line would be y minus 1/4 equals slope x plus 1/2. There's the equation of my tangent line through negative 1/4. Over here, I'm going to do the same thing. I have a point in 1, and my slope will be 2 times whatever my x value is, which in this case is 1. So I get a slope of 2. So the equation of my tangent line going through 1, 1 is going to be the following. So in general, the slope of PQ, which is the average rate of change of f of x from P to Q, right, represented by this line here, is an average rate of change, where if we want to find the slope of the tangent line at point C, we're going to find the exact rate of change, or the instantaneous rate of change, at x equals c. The derivative gives us the value of the slope of the tangent line to a curve at any given point, or at a given point. The derivative of the function f with respect to the variable x is the function what we call f prime. Right? This right here we call f prime, whose value at x is the limit as h goes to 0 of the difference quotient. The alternate definition is the derivative of the function f at the point x equals a is this limit. So the derivative at a point A is this alternate form of the difference quotient, but what you'll notice is that the limit is not where h is approaching 0, it's now where x is approaching a. Another way to write that, which is very similar to what we saw above, is the limit as h goes to 0 of f of a plus h minus f of a over h. So let's apply this. If f prime exists, we say that f has a derivative, meaning it's differentiable. So if I ever ask you to differentiate f of x, that means take its derivative, right? Use that difference quotient and take the limit of the difference quotient as h goes to 0. A function that is differentiable at every point on its domain is a differentiable function. Okay, so what that means is that their derivative can be calculated anywhere on that function. So let's take and let's find f prime for x squared plus 1. So f prime of x, which is the derivative at any point x, is equal to the limit as h, that's an h, goes to 0 of f of x plus h, so it'll be x plus h quantity squared plus 1, that's f of x plus h, minus f of x, which is x squared plus 1, all over h. So if I expand the numerator, I'm going to get x squared plus 2xh plus h squared plus that 1 minus x squared plus 1. So f prime of x, or the derivative of f of x, will be the limit as h goes to 0 of the following. Alright, so we're going to get some cancellations here. Okay, so f prime of x will be the limit as h goes to 0. I'm going to take a different algebraic method here real quick. I'm going to take an h out of everywhere. Okay, so I'm going to take an h out of each of those terms. So if I take out an h, I get 2x plus h. I just wanted to take an h out of the numerator, right? So what we see is that the h in the numerator that I took out of both terms will cancel with the h in the denominator. And what we get is we get that the limit as h goes to 0, which as h goes to 0, that will go away. We see that the derivative will equal 2x. Now what's interesting about this is we got the same thing for x squared. But how's that possible, right? So here we've got x squared, and here we've got x squared plus 1. What you'll notice is that even though we've added a constant on, right, we had y equals x squared, and then we had y equals x squared plus 1. Nothing has changed with the slopes. Okay, the slope at x equals 1 is going to be the same at the slope on both functions, right? So the derivative function is the same for both. Let's apply this using the alternate definition for the next one. Okay, so I've written out the alternate definition of the derivative, which is the limit as a approaches x of f of x minus f of a over x minus a. So let's do a little algebra there. So that'll be the limit as a approaches x of f of x, which is square root of x, minus f of a, which is the square root of a, over x minus a. And I'm going to employ one of my methods that we learned earlier on, which was I'm going to multiply by the conjugate. And the conjugate of x or square root of x minus square root of a would be the square root of x plus the square root of a on the top and the bottom. So let's go ahead and do that. Let's do a little algebra on it and see where we get. When I FOILed the conjugates in the numerator, we got x minus a. So what we'll see is we get cancellation here. And as we take the limit as a goes to x of 1 over root x plus root a, we would just do a direct substitution. And that direct substitution would be plugging in an x for a. So it looks to me like we get, after that direct substitution, we get 1 over root x plus root x, which is 1 over 2 root x. And that's our derivative of the square root of x. Okay, so a little bit of notation. These are different ways to write the derivative. Okay, you can look at these on your own time. The most common to see are probably these three. Each of those means the derivative. These are a little less common to see. I don't think I've ever seen that one before. This is not as common to see. And this right here is unique. What that's telling you to do, d dx, is an operator. It's telling you to perform the derivative on f of x. So if I said evaluate or perform d dx of x squared, as we saw earlier, the derivative of y equals x squared is 2x, so that would equal 2x. Okay, so each of these has just a different origin, different person came up with writing this notation, but each of them means the exact same thing. The derivative of the function f of x in terms of x. All right, that's 3.1.